Heat transfer problems are often classified as being steady, that is called the steady state, or the transient, which is called unsteady state problems. The term steady implies no change with time at any point within the medium, while the transient implies the variation with time or the time dependence. Let us take an example to understand the transient as well as the steady state heat conduction process. In this diagram, as you can see, at the time 2 p.m., the one side of the wall has a temperature of 15 degrees centigrade and the other side of the wall has a temperature of 7 degrees centigrade. Now with the passage of time, when the time passes from 2 to 5 p.m., right, and the temperature of the one side of the wall is 12 degrees centigrade, it means that it is reduced from 15 to 12 degrees centigrade, and the temperature on the right hand side of the wall is also reduced to 5 degrees centigrade. So it means that the heat conduction is a function of time, right? So with the passage of time, the heat or the temperature on the side of the walls changes. So it means that the heat conduction in the wall 1 and heat conduction in the block 2 is not equal. It means that this is a classic example of transient heat conduction. Whereas in case of steady state problems, the one side of the wall has a temperature of 15 degrees centigrade and the other side of the wall has a temperature of 7 degrees centigrade at 2 p.m. right? Whereas at 5 p.m. after the 3 hours time, the temperatures on both sides of the walls are also same. It means that there is no change in temperature with respect to the time. So it means that the rate of heat conduction on both of the walls are equal. So this is the example of steady state heat conduction. For example, heat transfer through the walls of a house will be steady when the conditions inside the house and outside the house will remain constant for several hours. The cooling of an apple in a refrigerator, on the other hand, is a transient heat transfer process, since the temperature at any fixed point within the apple will change with time during the cooling process. In heat transfer analysis, some bodies are observed to behave like a lump whose interior temperature remains essentially uniform at all times during the heat transfer process. The temperature of such bodies can be taken to be a function of time only. The heat transfer analysis that utilizes this idealization is known as the lumped system analysis, which provides the great simplification in certain classes of heat transfer problems. Consider a small hot copper ball coming out from the oven. As you can see in this diagram, measurement indicates that the temperature of the copper ball changes with time, but it does not change much with position at any given time. Thus, the temperature of the ball remains uniform at all the time, and we can talk about the temperature of the ball with no reference to a specific location. Let us go to another example that consider a large roast in the oven. As you can see in this diagram, if you have done any roasting, you must have noticed that the temperature distribution within the roast is not even close to being uniform. You can easily verify this by taking the roast out before it completely done and cutting it in half piece. You will see that the outer parts of the roast will well done while the center part is barely warm. Thus, the lumped system analysis is not applicable in this case. Before presenting a certain criterion about the applicability of the lumped system analysis, we developed a formulation associated with it. In order to understand simply the lumped system analysis, or what is the lumped system, so during the transient heat transfer, the temperature normally varies with time as well as the position. In special case of variation with time, but not with position, the temperature of the medium changes uniformly with time. Such heat transfer systems are called the lumped systems. A small metal object such as a thermocouple, junction, or a thin copper wire, for example, can be analyzed as lumped system during a heating or the cooling process. Geometry and parameters of lumped system analysis. Consider a body of arbitrary shape with a mass of m. For example, this pink color is a solid body, arbitrary shape, and having a mass of m, and the volume V with the surface area AS and the specific heat Cp, and consider that this body is initially present at the temperature of Ti, right? And at the time T is equal to 0, it means that body is placed in a medium at a temperature of T, right? And the heat transfer takes place between this body and its environment, and definitely the heat transfer coefficient will be represented by H. So for the sake of discussion, if we assume that this temperature T infinity is greater than this initial temperature of the body, what will happen? The heat will flow towards the body. In the opposite case, if the initial temperature of the body is higher as compared to the outer environment temperature, what will happen? The heat will flow from the body to the outer environment, right? So in order to understand, or in order to consider this a lumped system, we will say that the heat will either flow into the body or out of the body depending upon the temperature difference, but the temperature will remain uniform throughout the body. Then we can say that this is our lumped system. So the temperature will only change with respect to the time. So as the time passes, the temperature of the body will change uniformly, and either its temperature will increase or decrease. It depends upon the temperature of the body and the outside temperature. For the previous arbitrary shaped body, if we say that during a differential time interval delta T, the temperature of the body rises by the differential amount of temperature, that is dt. So we can apply the energy balance of the solid for the time interval dt, and it can be expressed as the heat transfer into the body during the time interval dt. And what will happen? It will increase the energy of that body. So the increase in energy of the body during the time delta T. So it can be expressed in the mathematical form. So this side is simply known as the Newton's law of cooling, right? And this is mCp delta T, the amount of energy which is basically stored inside the body in order to increase its temperature. So what we can do is we just split this mass into density into volume, and this delta T, the change in temperature, can be referred as the change in temperature T and minus T infinity. T is the temperature of the body at particular time, and T infinity is the surrounding temperature, and T is always constant. So the above equation can be rearranged in this way, right? So this is the differential form of the equation. We can integrate this equation by taking the limits. So after integrating this equation, we will have the final form of the equation just like this way, and this is the equation which is natural log of the temperature, which is a function of time, and minus the T infinity is the outer temperature over the Ti, that is the initial temperature of the body, minus the T infinity, which is the outer temperature, which is equal to minus HAS over density multiplied by volumes heat capacity into time. So if we take the exponential of this equation 4.3 on both sides, what we will have? We will have this form of the equation, right? And here we have just introduced a small constant which is B, and it is basically represented by these parameters, and it is actually a positive quantity whose dimension is per unit time. The reciprocal of B is obviously the unit of seconds, and it is also called the time constant. So from this equation we will just try to plot some graphs, and we will see that with the passage of time how the temperature of a particular body will changes, right? And it also depends upon the initial temperature of the body and other parameters as well. So the above equation can be plotted on this graph while taking the temperature on x-axis and the temperature on y-axis. So Ti is the same for all the cases, right? So what we are doing is we are changing this time constant values, right? So the above equation enables us to determine the temperature of the body at a particular time t, or alternatively the time t is required for the temperature to reach at a specific value of temperature. So if the value of b, that is constant, is very small, so it will take a lot of time for the body to reach at certain temperature. So whereas in the opposite case, if the value of the b is very high, so the body temperature will reach at a certain value in a shorter time. So what we have concluded from this graph, that the temperature of a body, a certain temperature of the body, can be attained based on this constant value. So the time constant is small, so it will take longer time to reach at a certain temperature. If the time constant is very high, so it will take a shorter time to reach at this temperature. So it can also be seen from here, right? So if the b, which is very small, so it will take a longer time, this much time, right? This much time to reach at a particular temperature t infinity. And if the b3, which is time constant, is very high for this graph, so it will take less time compared to the first one to reach at this temperature. Criteria for the lumped system analysis. The lumped system analysis certainly provides the great convenience in the heat transfer analysis, and naturally we would like to know when it is appropriate to use it. The first step in establishing the criterion for the applicability of the lumped system analysis is to define the characteristic length. So the characteristic length can be defined as the volume of a particular body divided by the surface area. So volume has a unit of meter cube and the surface area has a unit of meter cube. When we divide the volume by its surface area, so it will give you the characteristics length. So for example, this is a particular body, a solid body, and it has a volume of v and a surface area of as. When you divide the volume with the surface area, you will get the characteristic length. So here is an important Biot number that can be used for the lumped system analysis. So what is Biot number? Sometimes it is called Biot number, and some says Biot number. It is up to you. What do you say about this parameter Biot number? Biot number is the ratio of heat convection divided by the heat conduction. So Biot number is the ratio of heat convection divided by the heat conduction. So it can also be expressed as the convection at the surface of the body divided by the conduction within the body, right? So it is just simply represented by the convective heat transfer coefficient, characteristic length, over K, right? So this is the overall formula, and delta T and delta T will be cancelled out, right? And you will have the simplified formula of the Biot number, H, the heat transfer coefficient, convective heat transfer coefficient, multiplied by the characteristic length and divided by the thermal conductivity. Another formula is also given at the bottom for the Biot number. The lumped system analysis. So the first step in the application of lumped system analysis is the calculation of Biot number and the assessment of the applicability of this approach. So whenever you go for the problems in the transient heat conduction, first you have to calculate the value of the Biot number, and from the answers of the Biot number you have to analyze that whether you are assuming the lumped system or not. So here is the classical example of the calculation of Biot number. Let us say this is a spherical copper ball which has a thermal conductivity value of 401 watt per meter per degree centigrade, and it has diameter of 12 centimeter, while the convective heat transfer coefficient is 15 watt per meter square per degree centigrade. So you have to calculate the Biot number. So from the answers of the Biot number, you have to assume that, or you have to say that this is the system that we can consider for the lumped system analysis. So the first step in order to calculate the Biot number is you have to calculate the characteristic length, LC. It is the ratio of volume divided by the surface area. So the volume of a sphere is 1 over 6 pi d cube, and the surface area of this sphere that is pi d square. So after simplifying that, we will have the characteristic length 1 over 6 multiplied by d. When we put the values, and ultimately we will have the characteristic length that is 0.02 meter. When we put the values of thermal conductivity, convective heat transfer coefficient, and the characteristic length, we will have the value of Biot number that is 0.00075, which is far less than 0.1. So 0.1 is an important number. It is generally accepted that the lumped system analysis is only applicable when the Biot number is less than or equal to 0.1. So whenever you are using the transient heat conduction, you have to solve for the Biot number. If the Biot number value is less than or equal to 0.1, so you can assume that this is a lumped system. Otherwise you cannot consider this is a lumped system. Note that the Biot number is the ratio of the convection at the surface to the conduction within the body. So as I have already explained that the Biot number is the ratio of the convective heat transfer divided by the conduction within the body, and this number should be small as possible for the lumped system analysis to be applicable. As I have already explained that the Biot number must be less than or equal to 0.1. So if the Biot number is less than or equal to 0.1, so we can assume the particular system as a lumped system for the understanding of the transient heat conduction. Therefore, small bodies with high thermal conductivities are good candidates for the lumped system analysis, especially when they are in a medium that is a poor conductor of heat, such as air or another gas. The hot small copper ball placed in quiescent air discussed earlier is most likely to satisfy the criterion for the lumped system analysis. So let us try to understand this transient heat conduction by an example. So this example basically explains the temperature measurements by the thermocouples. Let me just read the question statement that the temperature of a gas stream is to be measured by the thermocouple whose junction can be approximated as 1 millimeter diameter sphere, as you can see in the diagram. This is a thermocouple and it has a tip of 1 millimeter diameter, and its temperature is a function of time, and the gas is moving in this direction. So this thermocouple will be used to determine the temperature of this gas or the air. The air is moving in this direction, so obviously the heat transfer by the convection process is involved. So this H is the convective heat transfer coefficient, which is given in the question statement, which is 210 watt per meter square per degree centigrade. So the thermal conductivity of this tip of the thermometer is also given, that is 35, and the density of the air and the Cp is also given in the question statement. What you have to determine is how long it will take for the thermocouple to read 99% of the initial temperature difference. Solution: the temperature of a gas stream is to be measured by a thermocouple. The time it takes to register 99% of the initial delta T is to be determined. So we have to take some assumptions that the junction is spherical in shape with a diameter of D, which is 0.001 meter. Number 2, the thermal properties of the junction and the heat transfer coefficient are constant. And number 3, we will neglect the radiation effects and the radiation heat transfer. So the properties of the junction are given in the problem statement. We don't have to look for properties of the junction. So first of all, we'll have to go for the characteristic length. So characteristic length, in order to determine the characteristic length, we must have the volume as well as the surface area of a sphere, which is the tip of the thermocouple. So as you can see that this is the volume of the sphere and this is the surface area of the sphere. After simplifying that and putting the value of the diameter, we will have 1.67 multiplied 10 raised to the power minus 4 meter, and this value is the characteristic length. So after that we have to put this characteristic length value into the formula of the Biot number. So after putting the values, all the values, that is characteristic length, convective heat transfer coefficient and the thermal conductivity, we will have the value of the Biot number, which is 0.001, and it is less than the criterion for the lumped system. So in this case, the lumped system analysis is applicable and the error involved in this approximation is negligible. In the opposite case, if this Biot number value is greater than 0.1, so we cannot take this system as lumped system analysis. So this is the criteria. The Biot number must be less than 0.1. In order to read the 99% of the initial temperature difference Ti minus T infinity between the junction and the gas, we must have this expression. So for example, when the initial temperature, let us take an example, is 0 degree centigrade and the surrounding air temperature is 100 degree centigrade, a thermocouple is considered to have the read 99% of the applied temperature difference when its reading indicates that 99 degree centigrade. So when you put the 99 over here and 100 over here and 100 over here and the Ti is 0, you will have this value, that is 0.01. In order to determine the time to reach that particular temperature for a thermocouple tip, we have to use this formula, and everything is given in this formula, but we have to determine the value of B, which is the constant. So the values are given for this constant, the convective heat transfer coefficient, the surface area, and the density, the heat capacity, everything is given. So area and the volume can be replaced with the characteristic length, and remaining all the parameters are given, and you will have the value of B, that is 0.462 per second. After putting this value into this formula, you can easily calculate the time, which is equal to 10 seconds. Therefore, we must wait at least 10 seconds for the temperature of the thermocouple junction to approach within 1% of the initial junction temperature difference. Here is another example which involves the predicting of the time of death. For example, a person is found dead at 5 p.m. in a room whose temperature is 20 degrees centigrade, whereas the temperature of the body is measured to be 25 degrees centigrade when found. So the heat transfer coefficient is estimated to be H, the convective heat transfer coefficient, is equal to 8 watt per meter square per degree centigrade. Modeling the body as a 30 centimeter diameter and 1.7 meter long cylinder. So these are the dimensions of that particular dead body. So estimate the time of death of that person. A body is found while still warm. The time of death is to be estimated. For that we have to take certain assumptions. So the first is the body can be modeled as 30 centimeter diameter and 1.70 meter long cylinder. So these are the dimensions which is given in the question statement. The thermal properties of the body and the heat transfer coefficient are constant. The radiation effects are negligible. It means that the radiation heat transfer for this particular case is negligible. The person was healthy when he or she died with a body temperature of 37. So let us try to understand the properties of the given system. For this particular human body, we have to determine the properties. So we can say that the average human body is 72% water by mass, and we can assume the body to have the properties of water at the average temperature. So this 37 is the average human body temperature, and the dead body has a temperature of 25 degrees centigrade, and we can add them together and taking the average, which will be 31 degrees centigrade. So we have to determine the properties of that human body at 31 degrees centigrade, which is the thermal conductivity and the density and the specific heat, and it can be taken from the table A9. The first thing is we have to determine the characteristic length. So the formula for the characteristic length is the ratio of the volume divided by the surface area, and by putting the values in all the formulas, so we can have this characteristic length, which is 0.0689 meter. After getting the value of characteristic length, we have to determine the next is the Biot number. The Biot number is the ratio of H multiplied by characteristic length divided by the thermal conductivity. So we have the convective heat transfer coefficient in the question statement, and we have the characteristic length, and we have the thermal conductivity, which we have calculated earlier by taking the average temperature 31 degrees centigrade. So after putting all the values, we have this Biot number, that is 0.89, and which is greater than our criteria for the lumped system analysis, 0.1. Therefore, the lumped system analysis is not applicable. However, we can still use it to get a rough estimate of the time of death. So the exponent B in this formula can be calculated, that is by putting all the values of convective heat transfer coefficient, density, specific heat, and the characteristic length. We have the constant value, the exponent B, which is 2.79 into 10 raised to the power minus 5 per second. And after putting all the values, right, so the final body temperature is 25 degrees centigrade, and the room temperature is 20 degrees centigrade, and the initial temperature of the body, that is the average human body temperature, is 37 degrees centigrade, and we have the value of B, and ultimately we can solve it for the time. So the time would ultimately come 43,860 seconds, so it will be equal to 12.2 hours. Therefore, a rough estimate that the person died before about 12 hours before the body was found, and thus the time of the death is 5 a.m.